very much indeed. Well, it's a pleasure to be here. I hope you can see the slides now. Is that right?
Yes, we're good.
Very good. Okay. So this is a talk that I first gave 2 or 3 years ago, just before the pandemic, actually. And a former student of mine was organizing a conference, and they wanted a public lecture. And he told me they wanted a really big name to give the public lecture. And then he told me that the budget was a bit squeezed, so they were going to ask me instead. So with an invitation like that, you couldn't really refuse. And so I decided I'd give this lecture. But he also asked me, well, would I talk about things like wormholes and warp drives and time travel and all of that sort of thing? And what I said was, well, I would feel I could, but I was a bit embarrassed about that because there were so many exciting things happening in general relativity and observationally in general relativity that I'd rather talk about the real science as opposed to the science fiction. So that's what I actually did. And so we're going to spend this evening learning a little bit about what Einstein did 100 years ago. He revolutionized our understanding of space and time and gravity, which came from Newton. And there are some really extraordinary predictions that this theory makes. And what's really extraordinary is the way they've been tested experimentally in the last few years. So that's what I really want to get across to you this evening, and also something of how general relativity actually works. So there will be some formulae from time to time. So the plan is this. I'm going to talk about space-time, the what, where, and when of general relativity. I'm going to then describe one of the major effects of GR, which is the time dilation effect. And the punchline of this is why you might want to lie down, particularly after the formulae. We'll talk about black holes and whether you can see them, and then time machines, just for a bit of fun at the end. And you can summarize this as the extremely strong, the extremely weak, and the extremely odd faces of gravity. So that's the plan. And since we're a small group, by the way, I think if there are questions as we go along, I'm very happy to take them. Okay, so let's begin with space-time. And this is really where we want to describe events. So let's take an event, some silly little green spot flicking on and off. So that's something happening. But in order to be quantitative, we need to put some numbers on this to say where it is and when it's doing that. So we can describe the position using some coordinates, and we might use Cartesian coordinates, so an x and a y coordinate. So x is 4 and y is 3. That's where it's happening. But of course, there are many other things we could do. We could use polar coordinates, for example. We could say, well, it's at radius 5 and angle at about 37 degrees. So that tells us a bit about where it is. And the important thing is that the actual coordinates carry no physical significance in their own right. They're just labels for telling us where things are happening. So that's where, but we also want to say when. So we can basically think of each instant of time as being like a frame in a movie. And if we stack up the frames, we build space-time. So the whole movie in one go, which, since we had two dimensions of space and now we've got one of time, is a sort of three-dimensional picture of this event. Okay, so it's still the same silly light flashing on and off, but now it looks like this in space and time. So this idea of the stack of frames is really fits with Newton's idea of absolute time. And that's the sort of foundation of physics as we learn it from Newton. But one of the big things about Einstein's theory is that there is no such thing as absolute time, which is something we'll come to later. So for Einstein, time is just another coordinate, and we can slice up the space-time in many different ways. And each of those slices would have any justification, have the same level of justification to be called an instant. So this goes nicely with Douglas Adams's line, which I'm sure you've come across: time is an illusion and lunchtime doubly so. So nonetheless, for the moment, I'm going to hang on to the idea of Newtonian time. So we'll be able to talk about instants and see if we can do a little bit more physics before moving to general relativity. So here's the idea of a world tube. If we have an object, and it's moving in space-time, it actually traces out a tube. So here we have a body which is moving across the XY plane. And if we look at it in space-time, we get a sort of tube, and it's tilted because it's moving along. And the faster it moves, the greater the inclination of this tube away from the vertical. Okay, so that's something to hang on to. And by the way, are you seeing the whole grid of pictures at the bottom of the screen? I suppose you are, because I'm sharing my entire screen. Is that right?
We can't see the whole grid of pictures, but we can see your presentation, and it's moving nicely.
Ah, right. Okay. All right. I've got the grid of pictures sitting on top of that, but there we are. Okay. So now let's look at one effect that's nicely described by these space-time diagrams, and that's the Doppler effect, which I'm sure you're all very familiar with. If you have a speeding motorbike going past you, as it passes you, the pitch drops. Okay, the sound drops. And the same occurs if you move towards a stationary sound source. The pitch drops as you pass it. And we can illustrate this using space-time diagrams in the following way. So here we have a source, which is going to be S, and a receiver, which is going to be R. And on the space-time diagram, so time is going up the screen here, and space would be going along, so only one dimension of space. The source is emitting pulses of sound at regular intervals. So here, each green line leaving the line here, S, is one of these pulses being emitted. And because the speed of sound, or whatever it is being emitted, is constant, we get these straight lines. So these are the trajectories of the pulses. Okay? So they get received at the receiver a little bit later than they were sent out. Okay? So that's the picture. And if the source and receiver are at rest relative to one another, then the interval between the pulses as they're sent out is the same as the interval between the pulses as they're received. So you'd hear the same frequency as the source. Okay, so now let's look at two diagrams. In fact, let's look at this one because I think it's easier to see the effect actually. So here we have a receiver that's moving away from the source. Okay, so that's why the receiver line is inclined away from the vertical, because it's got some motion. And let's look at the pulses. So here's first pulse and there's the second pulse. And at the source, they were separated by our interval TS. Let's see where they cross the line of the receiver. Well, there's the first one, and here is the second one. And we notice that the interval between them is much larger than the interval at which they were released. Okay, so, and we can see that very, very clearly on this diagram. And on the other side, here we have a situation where the receiver is moving towards the source, and it's a little harder to see on the diagram. I guess you can just about see that the interval between resection of the two pulses is smaller at the receiver than it was at the source. Okay, and this is just simple geometry, but we can read out from it a physical effect. So if they're moving towards each other, the pulses are received at a frequency that's higher than the emission frequency. And this is by a factor 1 plus v over c, where v is the velocity of the receiver towards the source, and c is the speed of the pulse, which might be light, or it might be sound, or it could be waves in water, anything really that will transmit pulses. So this is blue shift, and as astronomers, you will all be familiar with that phenomenon. And if they're moving away from each other, then of course the pulses are received at a lower frequency, and that frequency is 1 minus v over c. That's the redshift of the signal. Okay, so that's the Doppler effect, and I think space-time diagrams give a very nice way of seeing that this what the effect is. Okay, so now we can move to general relativity. Keep an eye on the time. So this was developed in 1915 by Einstein. As you probably know, he came up with special relativity in 1905. And from about 1907 onwards, he was trying to develop a theory that would incorporate gravity. And it took him until 1915. He made many mistakes along the way. He hit on good ideas and sometimes then threw away the good ideas in favor of not so good ideas and was held back for years. So Einstein found this very hard to develop as a theory. But what he got in the end is really quite a beautiful piece of mathematical physics. And even better, it actually describes the world in which we live, really to a good level of accuracy. So let's see what it is. Well, he founded general relativity on a principle called the equivalence principle. And the idea is that physics should be the same in all freely falling, non-rotating laboratories, at least if they're small enough. And this is a heuristic principle, so Einstein doesn't tell you how small is small enough. Okay, but the idea is that if you've got a small laboratory and it's falling and freely falling, non-rotating, then an experiment you do in that lab should give you the same results as if you did the same experiment in any other freely falling, non-rotating, sufficiently small laboratory. So the punchline from this is that the best place to enjoy physics is in a falling lift. You don't have long to enjoy it, but this is where you can actually experience the laws of physics in their freely falling form. And another way of enjoying the laws of physics is to do what Stephen Hawking did here and take a ride in one of these switchback aeroplane trips. Okay, so there is Hawking enjoying zero gravity. This is all that matters. If you are in such a lab, then you will get the same results. Okay, so that's the idea of the equivalence principle on which Einstein founded relativity. So here it is again. If you think about it, you really need a way of being able to compare what goes on in different labs, because different physicists inhabit different laboratories. They need to talk to each other and explain what they've seen, and they need to be able to reproduce their experiments. So this idea of being able to compare what goes on in different laboratories is critical for the success of physics. But we also, of course, need some experimental evidence to say that this form of the equivalence principle, that it's the same in freely falling, non-rotating labs, actually gives you some physical predictions that you can test. Okay, so that's what we would like. And the remarkable thing is that you can find physical effects that are derived from this equivalence principle. And one is this idea of gravitational time dilation, which is that if you have two clocks in a gravitational field, then they actually run at different rates. And if one is actually higher than the other one. Okay, so let us see if we can understand this phenomenon. So let's consider two situations. We've got a box and we've got an observer. The observer gets to be a dot and the box is a red square. And in the first situation, we're going to have that the box and the observer are at rest. There's no gravity, there are no forces, and the observer accelerates towards the box. Sorry, I should have, that's happening there. Okay, so this little dot is accelerating towards the box. So the second situation is going to be similar, except the observer stays at rest and the box drops on it. Okay, so the difference is, as it were, who is accelerating towards whom. In the second one, the box is freely falling under gravity. So those are the two scenarios, and we're going to examine an experiment in both of them and compare. So, as seen from the box, in both cases, the observer is accelerating towards the box. But the box is a freely falling laboratory in both cases. In the first case, there's no gravity, so it is freely falling. and in the second, well, there was gravity, but the box was just freely falling. So the equivalence principle tells us that we should get the same results from experiments in these two scenarios. So let's examine an experiment. So now I'm going to draw it. Gravity, the difficulties of drawing this, time is going to go up, and the horizontal is actually, if we go towards the right, that's actually supposed to be going vertically down in space. Okay, I want to keep time as the vertical axis in all of these diagrams. Okay, so if you fall, you're going to go that way. So let's consider the first scenario. We have the observer initially at rest to one side of the box. There's the bottom of the box, and here's the top of the box. And at some time, a flash of light is sent from the top of the box to the bottom of the box. And let's the speed of the light be c. And of course, it hits the bottom of the box at some time. At the same instant that the flash is released, the observer is going to start accelerating towards the box. So it describes a sort of parabola. And eventually, of course, it hits the bottom of the box. And we arrange it so that it does that, so that it arrives at the bottom of the box at exactly the instant that this flash of light goes through. Okay, so the observer is there exactly in the right place to see the light. So we know how long this takes, of course, because it's the distance across the box divided by the speed of light in this instance. So we know what time it took for this experiment to occur. Okay. During the time that it takes for the pulse to cross the box, the observer is picking up speed. So if their acceleration is a, then the velocity gained is time times acceleration, so it's ha divided by c, and we use the blue shift formula and say that the observer is going to see the light blue shifted by a factor 1 plus v over c, which is 1 plus ha over c squared in this situation. There's what v was. So that's the blue shift factor that our observer will see. But now let's consider the other situation. So according to Einstein, everything should be the same if the observer is at rest, but in a gravitational field, and we drop the box on the observer. We have the pulse sent from the ceiling to the floor across height h, and that the floor is passing the observer at the instant that the pulse is received. So the poor guy gets squashed, but at least he gets to see some light just at that last minute. Now, according to the equivalence principle, this has to be the same as in our previous situation. So the observer has to see light that's been blue shifted. And we know what the factor is. It's 1 plus v over c. The acceleration in this is now the acceleration due to gravity. So we get the factor 1 plus hg over c squared. So according to the equivalence principle, this observer will see light being blue shifted. Okay, and remember that this observer is just at rest in a gravitational field. Now we throw the box away because we don't actually need it. All that happened here is that a pulse was emitted from some height and it was received at a height which was h lower. Okay, so originally that's where the ceiling and the floor were, but we don't need them. The point is that this is where the observer was. And the source and the receiver were both at rest in the gravitational field. So neither of them think that they were moving. So there's no reason for this to be a Doppler shift. And so the observer, receiving this light at a bluer frequency than they were expecting, has to assume that the clock that was measuring the frequency must be running at a different rate depending on the height difference. Okay, so it sees the light being blue shifted and concludes that the clock running at the top of the lift or the higher height must be running faster. And this is the time dilation effect. And it's not just true of these pulses, it's true of all physical processes, whether they're clocks, chemical reactions, cell division, or whatever you like. It's running more quickly at a higher altitude and more slowly at a lower one. Okay, so the slogan, takeaway message is lie down for a longer life, because at a higher altitude, all the physical processes, including your cell division and so on, is running more quickly. Now, this can be tested, and it has been tested, and a remarkable experiment from 2010 used a height difference of only 33 centimeters. We have the acceleration due to gravity. This was done on the surface of the Earth, so it's 9.8 meters a second squared. Speed of light is 3 times 10 to the 8 meters a second, well, more or less. The frequency shift, fractional frequency shift, is this hg over c squared. It is 3.6 times 10 to the minus 17, or that many zeros followed by 36. Okay, so it's absolutely tiny, this frequency shift, but they measured it. So they used atomic clocks, which could measure down to this around, well, what it measured was 4 times 10 to the minus 17, but then you've got your error bar to go on that. And we can see it on this plot here. This shows the frequencies that they were getting when the clock was in the higher position. So here is the frequency, it's been normalized to 0 line, and there it is in the lower one, and we see that we have a frequency shift. And what's going on, of course, you've got the experimental results here. This is some sort of best fit. Here we also have the lower ones, there's some best fit to them, and you can really see that there's a difference. This is the gravitational time dilation at a distance you can have on your desk, 33 centimeters. So in the same experiments, they also measured a time dilation effect that comes from special relativity due to relative speed. And they managed to get that for relative speeds as low as 10 meters a second, or 22 miles an hour. So this is essentially cycling speed. So if you go by on a cycle past their lab, they can actually measure the time dilation effect that ensues. So these are absolutely remarkable experiments coming from exceptionally accurate clocks. Now, that was the best experiment available in 2019 when I first gave this talk. There's an update from this year, actually. There are now claims of measuring the gravitational redshift at millimeter scales, and that's a paper from February this year. I looked at the paper. I couldn't find as nice a diagram in their paper as in this old 2010 paper, so that's why I didn't update it. I think this one illustrates the effect very, very clearly. So that's the first remarkable observation that I wanted to tell you about, that we can, on the one hand, by essentially pure thought, go from the equivalence principle to the idea that there must be a gravitational time dilation, and then even more remarkably, go and measure this in a lab over tiny distances, 33 centimeters, or now even millimeters. So moving on, I want to tell you a little bit about black holes, which are one of the other extraordinary predictions of general relativity. So I already told you that you can't think of any particular coordinate system in space as being particularly significant. We could go from Cartesian to polar coordinates. There's no physical significance in that. They're just useful labels. And in general relativity, the same is true also of time. I mentioned that you could slice space-time any way you like, and any of those slicings would have equal justification to be called an instant of time. So if we can't rely on notions like time, how on earth can we proceed? Well, we think of the equivalence principle and think of the fact that if there are no gravitational fields, light is going to be moving in straight lines at a constant speed. And therefore, at least over small scales, in non-rotating, freely falling labs, light should be moving on straight lines. So by tracing out what happens to those paths of light as it travels over much greater distances, we can actually begin to learn about space-time in a physically significant way. Because if light is traveling along a certain path, then you can put a receptor along that path and you will see something. So this is physically significant in a way that coordinate value is not. Okay. So then we have the idea of the light cone. So at any point, we can imagine all the light rays that could possibly emanate from that point. And it is a fact, it comes from special relativity, in fact, that all massive bodies follow trajectories that are always inside the light cone. Okay, so at every point along here, you could draw the light cone, and this trajectory will always stay within the light cone at each point. So these are blue lines are the possible observer trajectories, and there we have the light rays scudding along the outside of this cone. So the idea is that in special relativity, where there is no gravity, the light cones have the same shape all over space-time. So you could line them all up like that. Okay, of course, at every point there's a light cone, so I've just drawn a few representative ones here. But the effect of gravity on the light cones is to make them tilt and vary in a varying way as you move around in space-time. So these cones can tip over. They can also close up or spread out. I didn't draw that, partly because it didn't look so good when I tried. But this, at least tilting, gives you the idea that they change from place to place. And this tilting and spreading or closing up of light cones is effectively an expression of the fact that space-time is curved. And for Einstein, gravity is curvature. And the Einstein equations, which I think I'm not actually going to write down for you, but they relate the curvature of space-time to its matter content. And that's the big idea or one of the big ideas in Einstein's general relativity. The more massive an object is, the more strongly the light cones are going to get tilted or closed up or what have you. And the extreme situation of this is the black hole. So let's have a look at a simple black hole model. This is to do with the Schwarzschild black hole from 1916. Schwarzschild was actually on active service. He was on the Eastern Front in the First World War. Obviously, he was a German. And Einstein had come up with the general relativity in 1915, but he didn't actually have any solutions. There were no, apart from flat space-time, which is rather boring. So Einstein had some approximations, but no actual solutions to his equations of general relativity. And Schwarzschild, despite being on the Eastern Front in the First World War, was also calculating these things in general relativity. He came up with the solution to the equations for a spherical distribution of mass. And you imagine you're sitting outside this distribution of mass. So this might be sitting outside a star, for example, or some other spherical body. So the idea is, and I'm not going to write down the formulae that actually show you the Schwarzschild solution. I'm just going to show you what happens to the light cones. And if we go a long way away over here, the light cones, so again, time is going upwards. So here is a point, and those are the light rays coming out of that point. These are only slightly tilted. And if we went to infinity, as it were, then there would be no tilting at all. It would just look like flat space-time. But the closer in we get, the more these light cones start to tilt. And so we see it over here. I put in some extra ones. We see the tilting becomes more and more severe until we get to this dashed line here, when all of the light cones are sort of so tilted over that this dashed line is actually sketched out by a light ray itself. Okay, So massive bodies, remember, they are always constrained to live inside the light cone. They all have to go across this line, and once they've crossed it, they can never come back. So this is what we call the event horizon. It is the surface from which even light itself can't escape. So if you're a photon, the best you can do is skim along this dashed line here. You can't get out. And everything else, all massive bodies, go in. And then there's something very nasty that happens at the red line, which is called a singularity, that I won't say a great deal about. But that's your ultimate fate, and you will hit that in finite time, according to your own watch. So that is the picture of a black hole, and that's how the light cones work. And so these blue lines are possible observer trajectories, and they all go in, and they all hit the singularity. Okay, so some facts and figures about black holes. So a star will become a black hole if its physical radius, so from the center to the surface of the star, is less than the Schwarzschild radius. Okay, and then that's because outside the star, this solution of Schwarzschilds holds, and so if the star is somewhere in here, then we have this event horizon sitting outside the surface of the star. So then you get the effect that things will get pulled in. So this is the formula for the Schwarzschild radius. G is Newton's constant of gravitation. M is the mass of the star. C is the speed of light. So that is how you work out the Schwarzschild radius. And if you do that for the sun, you get a distance of only 3 kilometers. And of course, the actual radius of the sun is around 700,000 kilometers. So the sun is very safely not a black hole. But if it were to shrink somehow, maybe towards the end of its life, to a distance less than 3 kilometers, it would be a black hole. And of course, and to do that, you would have to maintain the same mass, right? So we want all of that mass concentrated in a 3 kilometer radius ball. Now, this is, of course, an absolutely fantastically high density. And when these solutions were first written down, people thought, well, you know, this just could not possibly happen in the physical universe. This is so extreme. It must just be some peculiar mathematical aberration of the equations. And you don't believe it, okay? Because it just couldn't possibly happen. So, and also the idea of the singularity that just eats everything up. This was also thought to be a peculiarity, and that a real star, which is rotating and very complicated, that would not fall into such a simple situation. So people thought this was just a peculiarity. You wouldn't, it's nice to look at, nice mathematics, but it's not physics. But that view changed through the 1960s in particular, and it changed for several reasons. So in the mid-60s, there were theorems, mathematical theorems, proved by Roger Penrose and Stephen Hawking. And these indicated that the singularities were not just mathematical peculiarities of special symmetrical situations, but they're actually inevitable under a very broad range of conditions. So these were very famous theorems. They are mathematical, and they're within the theory of general relativity. And what I find particularly remarkable about it is that when Penrose proved his theorem, which was in 1965, there was no candidate for a black hole actually known. Okay, so it was genuinely an open question as to whether there were physical black holes in our universe. And I think the first candidate was from around 1970. The Cygnus X was the first candidate black hole that really gained traction. So you got this theoretical evidence that we might expect there to be black holes in the universe. There were also discoveries around the same time of neutron stars, which are of course extremely dense, not dense enough to be black holes, but very, very much more dense than people thought could possibly occur. We actually got these candidate black holes from about 1970. And as you all know, now it's believed that most galactic cores contain a black hole. So this brings us to 2020, so after I first gave this talk, and here we have the Nobel Prize for physics in 2020. It went three ways. Roger Penrose got a half of it, and that was for the discovery that black hole formation is a robust prediction of the general theory of relativity. So for these theorems that Penrose was first, and then Hawking adapted the theory, well, and then they collaborated together on various other singularity theorems. But Penrose was the originator of these singularity theorems. And then there are two others, Gensel and Gaze, and they were given the half of the Nobel Prize to share between them, so they each got a quarter, and that was for the discovery of a supermassive compact object at the center of our galaxy. And interestingly, the Nobel citation does not say it's a black hole. It just says it's a supermassive compact object. But anyway, I think everybody says it's a black hole. And this brings us to the movie part of the presentation. The black hole at the center of our galaxy is Sagittarius A star. You probably all know this a lot better than I do. It's 26,000 light years away from us. It's got a 60 million kilometer diameter and 4 million solar masses. So it's a big thing. And the way we identify it as a black hole is, or at least the way we know there's something there at all, and why we think it's a black hole, is to do with the way it affects the orbits of nearby stars. So this is the first video, and let's hope that this shares. All right. If it, Steve knows what to expect now. So if it doesn't come on, Steve, could you give me a shout?
Yes, I've got my eye on
it. Are you seeing it now?
Yes, that's
you are, right. So I need to move this out of the way, and then with any luck, there it is. Okay. Oops. So what we have here is a diagram of the orbits of various stars. You see S2's just whizzed around that thing. Keep an eye on the counter at the bottom. That's the year, the date. And S2 is going to come round again in about 2018. But meantime, there it goes, very quickly around the thing. Meanwhile, you notice that they're orbiting apparently nothing. So in this video showing the stellar field around the center of the galaxy, there's absolutely nothing to see, but something is making these stars orbit around it very, very fast. And we're focusing in on S2 for a reason, which will become clear. I'm always very nervous when these video adverts pop up because you never know quite what it's going to suggest. But fortunately, it's all right. Then we come back to the presentation. So that's why you might well believe that there is something there. Another reason is that you will get a effect on passing objects. And one is a gas cloud. Now, I apologize, I'm not sure if you're going to get the audio. There's a commentary with this one, but well, if you get it, then you get it. But if not, it doesn't matter. So here we go on this one, and to full screen. Oh, you get some music as well.
No one knows what will happen next. The cloud will probably heat up and may start to emit powerful X-rays as it gets disrupted. In the end, the material will eventually disappear by falling into the black hole. For the scientists, this event is truly a unique chance to probe the hot gas around the black hole.
So I'm just going to play, if I can find the beginning of that, now I'll tell you what's going on. So what happened was that the people who were observing it, in fact, there's Gensel and Gaze, who got the Nobel Prize, were of course very interested in this region around the Sagittarius A star. And they were astonished when they realized that there was a cloud of gas heading straight for this black hole region. So this cloud of gas, if I can find where it begins, oh right, so it's somewhere around, oh, there is Gensel himself. So there it is. It's some number of multiples the mass of the sun. It's made of hydrogen, and it's just a sort of cloud. It's around the place, and it is actually all heading for this black hole. So if we watch it, there we go. So that's 2011.
No one knows what will
yeah,
happen
okay,
next.
we get her.
The cloud will probably heat up and may start to emit powerful X-rays as it gets disrupted. In the end,
so I will stop it there. So you get this beautiful simulation of what's going to happen with the gas cloud. Now, actually, this is something I didn't have time to follow up before giving the talk tonight.
the material
Oh, sorry, she's back. Is to work out, see what has actually happened since, because this part of the simulation is actually now around the present day. Okay, so this first pass of the cloud around the black hole has happened, and so there should be data. Now, I just didn't have time to look into that, but if you want to do some improving reading, you could try to find out what happened to that gas cloud. Okay, so if we go back to the presentation, so that's why we think there's something there. It's clearly very big because it makes stars orbit around it. It pulls gas clouds apart, as we've seen. And again, more evidence that it's a black hole comes from some very recent observations, or 2019, on that star, SO2, or S2 it was on the previous video. Now, we saw it go round in about 2018. It reached the closest approach. It orbits on around a 16-year period, and they've been watching it for quite a while. So at that closest approach in 2018, they made various observations, interestingly, all Earth-based optical telescopes. And this star was doing 2.7% of the speed of light, okay, which is, well, pretty fast, actually. And that was the relative velocity. So that's the velocity relative to the black hole at the center of the galaxy. So this orbital speed is extraordinary. And it was fairly close as these things go. It was 120 Earth-Sun distances, astronomical units. So this was enough to make a marked redshift. Okay, they measured the redshift in the spectral lines, and by doing that, these measurements indicated that the results were consistent with general relativity to 1 sigma of significance, and Newtonian gravity is excluded at 5 sigma. So in other words, it would have to be extremely unlikely coincidence for Newtonian gravity to be the correct theory, but nonetheless to get the results that they did from this experiment. And I'm going to show you them now. Okay, so I like this diagram. It's another one that really shows what's going on. So here is the optical, the image that they got of the center. So it's nowhere near as pretty as the video I showed you. There is our SO2, and what you of course do is you look at the different spectral lines. So here we have the spectrum of light that's coming from SO2, and we notice that the flux of light varies with frequency, and in particular it's got a big dip here. This is one of the spectral lines of hydrogen, and presumably light is being absorbed in the star itself, so it just doesn't get out at that frequency. So there is a big dip, and that feature is a noticeable presence in all of these spectra. So what we've got here is the spectrum observed. This is 2017 in July, and then we move. Now let's get them in the right order. So let's see. So so later in time, we're just going straight up the page, in fact. So this is in July of 2017, and we see here is where the peak is. And by early 2018, we have this very high speed. The shift now is to higher wavelengths, so that's a red shift, and that's because the thing is moving away from us. And that became even more marked as you go through April. Okay, so that's the highest relative velocity to us. So really pushing out that red shift. Then it starts coming back towards us. So as we go through May, and then later in May, and by sometime in between May and July of 2018, it now switches. So in fact, the velocity is negative, which actually means it's moving towards us. And at that point, you can see that this spectral dip has got a smaller wavelength. So that's a higher frequency, it's a blue shift of the spectrum. So you can really see very, marked change in the spectrum of this star as we went past the I suppose you'd call it the peri, well, I'm not quite sure, peri whatever a black hole would be. So periastron if it was a star, is that right? But in this instance it's a black hole. So that is really quite extraordinary data. Again, it's from the last 2 or 3 years, and we get a really astounding fit with the predictions of general relativity. Okay, so that's the evidence for black holes. I'm just thinking if there's anything else. Oh yes, of course, the famous image from 2019. So another very recent thing. You'll all have seen this picture of the M87 star black hole image, and this is 55 million light years away. What we're seeing, the illuminated part here, this is ionized gas surrounding something, and there's clearly, again, as it were, nothing there. There's a big black emptiness inside this this ionized gas. So it's estimated that M87 is 65 billion solar masses. So it's a supergiant galaxy and a supergiant black hole in the middle of it. If you work out its Schwarzschild radius, that's 130 astronomical units. So that's quite big. General relativity predicts that when you look at a black hole, its apparent size is not the same as the Schwarzschild radius. It's about 2.6 times the Schwarzschild radius. So we expect the shadow of M87 to be 340 astronomical units, not the 130 that you would naively get from the Schwarzschild radius formula. If you do your best and try to estimate what the radius of that central black region is, you come up with 352 astronomical units. So we're in very much the right ballpark. I don't suppose they have very many digits of precision on the 6.5 billion solar masses. So to get as close as this is really quite remarkable agreement. So this is yet a further reason from recent observation to accept the theory of general relativity as a very fundamental part of what makes our universe tick. Yet another one, of course, is the advent of gravitational wave astronomy, because a further prediction is that if you have bodies in relative motion, then they will create gravity waves, sort of ripples in space-time. I'm not going to say a lot about this. You will have seen, doubtless, the pictures of the LIGO detector out in the desert. Here, these arms here of this detector are 4 kilometers long, and a typical gravity wave, when it comes through, distorts the length of these arms by about 10 to the minus 18 meters in the 4 kilometers. Okay, so it's a fantastic piece of experimentation that they can even detect this, and they have to screen out all sorts of other noise in a tremendous way. So to date, and this is, I checked this one earlier in the week, they have 90 gravitational wave events that they've catalogued to date. I mean, the first one was back in 2015. These are all from mergers of black holes or neutron stars. I think they also have neutron stars hitting black holes and things like that. So this also won a Nobel Prize in 2017, and it went to Rainer Weiss, Barry Barish, and Kip Thorne, who will come back in a little bit later in the talk. So that, I think, is all of the serious stuff. And now I think we move on to the fun stuff at the end. I did want to say just a little bit about time machines as the most extraordinary face of gravity. So let's take general relativity and more or less test it to destruction. Let's imagine that the light cones could be tilted round so much that you could have a curve like this that loops back and then could cross itself at some earlier point. So this would be a history of some object. It goes on a journey and then it gets to meet its earlier self. So that is how one could describe a time machine, if you like, in general relativity. And it's not just a matter of drawing pictures. There actually is, in fact, there are many solutions to the equations of general relativity that have this feature. And this is quite a remarkable solution. It was due to Kurt Gödel, who the logician, and he got very interested. He was at Princeton in an office not too far from Einstein. They used to spend a lot of time talking together, and Gödel decided he was going to come up with a solution to Einstein's equations. And the matter that he put in this space-time is essentially rotating dust. And the solution is engineered so that there is a line, that's the red line, where the light cones are tilted round so much that you can have a trajectory of a massive body that just loops round and round and round on this red trajectory. Okay, so what I've drawn here are in fact, the blue lines here, these are all possible paths of light, and you see it's a remarkably complicated and twisty sort of thing. And out here we have this closed time-like curve, as it's called. So if you were traveling along such a curve, you would be repeating your history on a regular basis. So how can we possibly make sense of all of this? Oh yes, well, here's the obligatory Doctor Who slide to indicate how else we might get time machines in the physical universe. Maybe there are things like wormholes where you have a shortcut from one location to another, and there's the long way round, and here you have a short way round. And in such circumstances, it's quite common that you find that there are loops that go around here, which are actually time-like curves. So it could be followed by a massive body and which repeats themselves, like the time machine picture. Okay, so wormholes would also generally give rise to closed time-like curves. Now, one of the things that always comes up when you start talking about time machines and time travel are the paradoxes. And something, of course, people have been discussing these in bar rooms since I don't know when, but what I think is quite nice is that general relativity gives you a way of actually turning discussions like that into mathematics. And when it's turned into mathematics, then you can find out what the resolution is. You can actually understand it in a way that's free of all the usual distractions. So let's have a look at a time travel paradox from the perspective of mathematics. So I'm going to give you one which actually is a logic gate. So let's imagine we have an exclusive OR gate. So as you know, this has got two inputs, A and B, and it's got one output. And here's the truth table. So if A and B are both 0, we get 0 out. If exactly one of A and B is 1 and the other one is 0, we get a 1 out. If they're both 1, then we get a 0 coming out. And of course, the usual thing when you're playing with electronics is you can put any inputs you want into this gate, and then you'll get the corresponding output. And for every pair of inputs, there is a unique and defined output. You just read it off from this table. So what David Deutsch, who is in Oxford, decided to do was to take this simple circuit and put a time machine in it. So he imagined, what if you had a time machine, connect it to the output, and use it to transport the output back in time, so it arrives at the input B. It's exactly the same point as the other input arrived. Okay, and then the question is, well, what would happen? Now, notice that the output O and the input B are now the same. They have to be. That's the whole point of this setup. And we see that that immediately excludes these two scenarios here, okay, because we can see that this would actually correspond, if you like, to the time travel paradox, because if B is 0, then O is 1, and then B would have to be 1, and that would be a contradiction because it's supposed to be 0. Or if B is 1, then the output is O, but then that means that B has to be 0 as well, and that's also a contradiction. So these are the time travel paradox situations in this red shaded part of the truth table. But from the perspective of mathematics and logic, there's another way of saying this, which is simply that there is no consistent output if the input is 1. A is 1, okay, because that is the common feature in these two situations. So, of course, we can also say, well, what would happen if we put A to be 0? And then another remarkable thing happens, which is that both of these two possibilities are consistent, and there's no way of working out which one is going to occur. Because if A is 0, well, B might be 0 and O is 0, and that's consistent, or B might be 1 and O would then be 1, and that's consistent too. So on the assumption that something happens, the information about what exactly is going to happen seems to be created from absolutely nowhere. So this is to illustrate the fact that we can take situations with sort of time travel paradoxes and analyze them from the perspective of mathematics or mathematical physics. This was a logical one. I'm going to give you now another movie, and this is a snooker table. So here I have a snooker table with a difference, and the difference is that in the right-hand cushion, I have installed a time machine. And the effect of the time machine is going to be that if anything hits that right-hand cushion, it gets transported 20 seconds back into the past and appears from the other cushion, okay? So it will appear 20 seconds earlier, but moving at the same velocity as it goes in there. Okay, so that's my clever snooker table. So now I'm going to shoot a ball across the snooker table. I'm just going to hit it straight across. And, well, nothing very exciting happens, does it? Of course, this is what you expect to happen. It's just going to go on a loop now. This is nothing to do with it. It's just showing it again. Okay, so you hit a ball across a snooker table. It doesn't go near the dangerous place, which is this right-hand cushion. So, of course, it just goes to the top of the ball, top of the table. But now let me fire the ball in exactly the same way. And we can see something else can happen as well. So here we go. It sets off. And at a certain point, it gets hit by another ball. And then it gets knocked into the right-hand cushion. Okay. So what happens when it goes into the right-hand cushion is it will be transported back in time by 20 seconds. Well, actually, that was some time ago. That's where we started, actually. So there is the ball emerging from the right-hand cushion. Okay, so it's got its clock on it. There you go. It's now up to 30. And as it goes in, it goes to about 21. Right, so now let's see that on the loop. Okay, so it comes out at 24. And knocks the ball, its earlier self, into the time machine in such a way that it can come out and then knock its earlier self into the time machine. And now the fun thing here is that the initial conditions in these two situations are exactly the same. This is just the same initial conditions. but with the different possibilities that the time machine makes possible. It's like the logic gate. There were two consistent possibilities for the same input in the logic situation. Here we have, well, I've shown you two, but in fact there are infinitely many possible paths with the same starting conditions. So physics becomes very strange when you have a time machine around the place. And I think this is nearly the end. Oh, sorry, there is a little bit more, because the obvious question is this time machine actually possible? Is it possible to actually have one? Now we face the annoying truth that gravity is very good at pulling things together, but it is not good at pushing them apart. And so if we look at one of these wormhole situations, if you go through a wormhole, as you go in, things are quite good because all the incoming paths have to converge to get down this throat. But at the other end, you expect the opposite to occur. So the outgoing paths have to diverge. So gravity is very good at pulling things together, but it's very bad at pushing them apart. So something strange has to happen. And the strange thing that has to happen is that somewhere inside, you need matter, which doesn't have positive energy density, as we're used to, but it has to have negative energy density. And that's how it can have the sort of reverse gravity effect of pushing stuff apart. So this turns out to be true that in many different attempts to build time machines, to think of descriptions of time machines within general relativity, you always end up needing this negative energy density. The problem is that, well, actually a possible way out is that in quantum physics, you can actually have negative energy densities. And an example of this is in the so-called Casimir effect. However, to spoil the party, it turns out that the negative energy densities you can get out of quantum field theory are limited in terms of their magnitude and duration. If you want a lot of it, you can only have it for a very short period of time. Or if you want it for a very long period of time, you can't have very much of it. And so this is an idea called a quantum energy inequality. It's something actually I've spent a lot of my career working on. It unfortunately spoils the party for many of these attempts to build time machines. Nonetheless, even though the likelihood is that time machines can't be built, it is extremely intriguing and thought-provoking to take a theory of physics and push it to its extremes. And we've seen this in the experimental work. These are extraordinary experiments, really at the limits of what can be done. And they have provided remarkable insights into the world that we inhabit. But, and it's fun to go even further and to think about things like time machines. As proof of that, and the reason that the stimulus that it provides to great scientists, I wanted to give examples of these three characters. So Stephen Hawking needs a little introduction. He was quite interested in time machines in the early 90s, did some very interesting work on them. Here we have Kip Thorne, and he won the Nobel Prize for the gravity wave work. But he also, in the 1990s, got very excited and interested in time machine work, just to understand how physics could be adapted to such a strange situation. And the last is David Politzer. Now, he also won a Nobel Prize, in fact, for quantum field theory, and he was yet another of the scientists working on time machine in the 1990s. So was I, but I didn't quite feature in this illustrious lineup. So I will leave you with that thought, that pushing physics to its extremes can be thoughtful, thought-provoking, and our theory of general relativity is a fascinating arena in which to do that. So thank you.
Right. Thank you very much, Chris. Very entertaining talk there. I thought you explained things extremely well. Though it's quite a difficult subject that you were trying to get across, but I think you made it as clear as it could have been. Can I just ask, are you happy to take questions?
Yes, certainly.
Yeah. So does anyone have any questions? And don't forget to unmute yourself.
Yeah.
Sorry, who was that?
That's James. Am I unmuted?
You are, yes. Yeah, sorry, I just couldn't see you.
Chris, that was fantastic, actually. I've got to congratulate you, especially on making the attempt and succeeding in the time dilation graphs.
Thanks. Good.
It's a bit of a vague question, but you touched on it at the end. So the general relativity has been so well tested at extremes, but it's clearly not. It assumes continuous space and all this kind of thing. So at the quantum level, there's something not quite right. Can you just kind of talk about? I'm not sure what my question is, but can you talk about bringing that together and your views, whatever?
You're absolutely right. So the mathematics that describes general relativity is what's called differential geometry, and it's the study of smooth spaces, really. And as you say, indeed, it's a continuum. So in general relativity, in principle, you could keep zooming in on an individual point, and space would continue to look like a continuum all the way down. And in fact, that's also partly what Einstein relies on, this idea of the equivalence principle, the sufficiently small labs, if it's small enough, and small might be really, really small, to make that work. Now, as you say quite correctly, we do not have a theory that combines gravity with the other forces of nature. The other forces are all described in terms of quantum theory, and in particular quantum field theory. Gravity has resisted attempts to make a nice description that is fully satisfactory. That's an ongoing research problem. You can have very many different views as to what space-time is actually like when you go to the smallest scales, and it is essentially open. Nobody knows, we can't probe it. Until very recently, there were very few tests of gravity even at millimeter distances. So it was in principle conceivable that below even millimeter scale, you might see a theory of gravity quite different from the one that we're used to on say, solar system scales, and terrestrial and solar system and cosmological scale. I think these millimeter scale tests are clearly saying that general relativity is holding its own down even to the millimeter scale, and maybe we'll get further. At the very smallest scale, there are all sorts of different ideas. There could be some sort of foamy structure. There might be structures with many wormholes, which is, I think, one of the reasons why people like Hawking and Thorne and Politzer were very interested in understanding physics when there's time machines, because perhaps at the smallest scale there are time machines, these tiny causal loops, and somehow you have to work out how on bigger scales we manage to do physics without all of the sort of paradoxical or problematic consequences of these closed time-like curves. It could be that space-time is a very much more discrete thing. There are people who work on things called causal sets, where all you have are sort of primitive ideas of an event, and all you have is the causal relations between them. So it's a very basic mathematical structure. And there are other ideas altogether that geometry might not be described by ordinary, as it were, the calculus that we're used to from school, from A-level, for example, but you have something called non-commutative geometry that even, you know, as it were, space-time coordinates start behaving in a way like quantum operators. So we have uncertainty relations between different between, say, the x coordinate and the y coordinate. Okay, so there are many different viewpoints on what space-time might be like at the smaller scales, and it's only really going to be resolved by experimental test. Somehow we have to get access to these tremendously small scales, and this is almost certainly going to have to be extremely small, because our particle physics experiments in CERN are effectively testing theories of physics at very, very small distances. They're very, very high energies, and that is very much correlated with small distance scales. So we're really working at tiny distances already, but it's going to have to be pushed yet further, and nobody knows how much further, because we don't have a theory of quantum gravity, but it's certainly going to have to be pushed further before we'll see any experimental signatures of what the different structure might be. Sorry, go ahead.
Sorry, so is this correct, that there's no experimental evidence whatsoever that general relativity fails at the smallest levels? Because it's too difficult to measure. But there's so much other stuff in terms of quantum field theory and all the other forces that suggest it would be really weird
yes.
if space-time was continuous for gravity, for general relativity, but not for anything else.
Exactly, because general relativity is a field theory. It looks very much like, quite similar to things like classical electromagnetism, which is a field theory. And we know what happened to classical electromagnetism. It became quantum electrodynamics. It's described by a quantum field theory. So you would really expect that a theory like general relativity would have a quantum aspect, and we simply don't know what it is. It is also possible, of course, that general relativity might be a bit like thermodynamics. So in thermodynamics, you deal with sort of gross properties of gas and fluids and so on, and you're not thinking about the microphysics. So you distinguish statistical physics, where you would try to keep track of individual particles and then try to understand phenomena like pressure, or you've got thermodynamics, where you only look at these sort of variables like pressure, volume, entropy, things like that, which are really taking a sort of coarse-grained view of what you've got in front of you. And it is quite possible that general relativity is like that, and that our description of space-time is such a coarse-grained description, okay? And then the real challenge is to sort of get below that and try to work out what the microphysics would be. And this is very hard. If you try to do it from thermodynamics and try to figure out statistical mechanics from there, I think you wouldn't have a hope. It's hard enough actually trying to go the other way, but thermodynamics gives you no clue as to what the underlying microphysics would be. So if it's like that with general relativity, we've got the wonderful description, which is going to be good at scales above who knows what, but certainly good enough for us and the cosmos. But the microphysics might be really quite different, and we've got no clues yet as to what that would be. Except
I feel very sorry for poor Mr. Einstein if it turned out that his general relativity was just statistical.
Yeah, well, like thermodynamics, yeah. Well, of course, he wasn't happy in the end, right? Because he wanted to have a combined field theory. So he spent the last decades of his life working on unification. And he didn't, and he never got anything that worked. He also wasn't very happy with quantum theory either, but that's another story.
I've seen an article in New Scientist this morning. It says crooked star clusters may be a sign that Einstein's gravity is wrong. And it's to do with, someone says that they've said that the modified Newtonian dynamics fits this thing where they've seen some stars escaping from a star cluster. Can you tell us anything about that? Because I don't have a subscription. I wasn't able to read it.
Okay, I don't know about this. I mean, I modified Newtonian gravity is one of very many attempts to do something that isn't general relativity, but make another theory of gravity. And it's important to have these theories because that's what you use to test gravity, general relativity against. Now, so I don't know about the crooked star cluster work at all, I'm afraid. Well, sounds interesting. Of course, that would have to be put in the context of a lot of other results as well. But I think what is true is that sooner or later there might be some, as it were, smoking gun, some observation that cannot be explained very well using general relativity, but might be fitted better by some other theory. And then that would set you off in some direction. I do wonder, as you know, one of the big mysteries is about dark matter and this idea that a huge proportion of the mass of the universe is invisible to us. So this, to me, I mean, I have to take the word of the cosmologist for it, but every so often I wonder, in 50 years' time, what will people think? Will they have figured out that actually the problem is general relativity isn't quite right, and that then they will look back and think that we were very naive for just saying, oh, well, you can't see the overwhelming majority of the universe. And then people might look back on us and say, well, it's like the people who made epicycles to explain the motion of the solar system. I think it was very primitive and erroneous position to be in. So yeah, I mean, it could happen. It could certainly happen, but I can't comment on that particular report.
Thank you.
Okay, thank you. I think we've kept you talking for quite a long time there, Chris. Yes, thank you very much again. Hugely entertaining talk, and thank you for a couple of very well explained answers there. So I think it just remains to ask us if we can give our thanks to Professor Chris Fewster in our usual way.
Thank you very much. Yeah.
Thank you very much indeed.